Hello and welcome to today's webcast brought to you by Laser Focus World. Today's event, the Silicon Photomultiplier Operation, Performance, and Possible Applications, will be presented by Slawomir Piatek, Chief Scientist at Hamamatsu. Before I go on with this introduction, I just want to mention that we're starting with a short two-question survey that you will see on your screen momentarily, or maybe now. Please fill it out, as the results will help our presenter tailor his presentation today. This presentation is both live and interactive, so you can ask questions at any time by clicking in the Ask a Question box in the presentation window and clicking the Submit button. And we do encourage questions. We will hold a short Q&A session right after the presentation. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it's recommended that you close down all other applications for best performance. For those in the audience who want a copy of today's slides, a PDF of today's presentation is available in the Event Resources section below the Q&A box. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.laserfocusworld.com. Now it gives me great pleasure to introduce our presenter, Slawomir Piatek.
Thank you very much, John. Hello again. My name is Slawomir Piatek. I am a physics university lecturer at the New Jersey Institute of Technology and technical consultant at Hamamatsu Corporation. We are going to spend the next about 60 minutes discussing a rather fascinating and rather new photodetector known as silicon photomultiplier, or SiPM in short. Very high intrinsic gain, together with minimal excess noise, makes silicon photomultiplier a possible choice of a photodetector in those applications where input light level is in the photon counting range. This webinar is a high-level review of SiPM's structure, operation, and optoelectronic characteristics. These topics will be followed by a discussion of 3 possible applications of SiPM. Here is the outline, which mimics my introduction. I would like just to point out that the 3 applications I'll discuss are Automotive Time-of-Flight LIDAR, where LIDAR stands for light detection and ranging, flow cytometry, and radiation detection and monitoring. Let's begin our presentation by looking at images of some silicon photomultipliers. These images are not to scale, but just to give you an idea, the active area, which is in gray, for largest SiPM is 6 by 6 millimeters. SiPM is a 2-pronged photodetector. One prong is an anode, and the other one is the cathode. Amazingly, its electric symbol is that of a ordinary diode, even though the 2 devices are very different from each other. Let's look at SiPM's structure. The current SiPMs are square arrays of square microcells, as shown on the left-hand side of this slide. In the middle, we see 2 views, a side view and top view of a single microcell. Below the oxide layer, we have a structure of avalanche photodiode. In case of SiPM, this avalanche photodiode will be operated in Geiger mode. Above the oxide, or looking at top view, this squiggly structure is a quenching resistor. The role of the quenching resistor is to quench Geiger discharges that occur in the APD. All practical SiPMs will also have a layer of resin on top. All of microcells are connected in parallel, as this figure indicates. Each microcell, in response to photon, effectively is a current source. Thus, a SiPM has one current summing node. Let's look at some specifications of SiPMs. The active area ranges from 1.3 by 1.3 to 6 by 6 millimeters squared. However, please note that this range is not continuous. Microcell size, also referred to as pitch, will range from 10 by 10 microns to 75 by 75 or even 100 by 100. The number of microcells can be calculated by dividing the active area by microcell size. And these will range from a few hundreds to a few tens of thousands. The last entry, overvoltage, is not really a specification, but a super important parameter that affects almost all characteristics of SiPM. And by definition, the overvoltage is equal to a bias voltage, that's the voltage that user must apply to SiPM for it to operate, minus the breakdown voltage VBD, which is a voltage characteristic to APD, which decides whether APD operates in Geiger mode or linear mode. Again, I remind the audience that in case of SiPM, the APDs will operate in the Geiger mode. The overvoltage must be positive, i.e., the bias voltage must be greater than the breakdown voltage. Let's look at operation of SiPM. Here, we've biased SiPM, its cathode, with the bias voltage. In response to photons shown with these red arrows, a microcell may quote-unquote fire, i.e., it produces a current pulse. This current pulse is going to flow out of the anode. We are going to convert this current pulse into a voltage pulse using a load resistor, and that voltage pulse then will be input into a voltage amplifier. On the right-hand side, we see a possible resulting waveform. If this waveform is due to a single photon, we call this 1PE or single photon waveform. The gain is equal to area under this curve, corrected for the gain of the voltage amplifier and the load resistor. Remarkably, for SiPM, gain is on the order of million. There's only one other photodetector with such high gain, and that is photomultiplier tube. No other photodetector has gain this large. Let's look at the waveform a little bit more closely. We can see a very rapid rise time, so very short rise time. And there are two components of the waveform. There is a fast component, which one may or may not see depending on the bandwidth of detection and also on the construction of SiPM. And then there is a slow component. The slow component refers to a situation where a microcell is recovering from a discharge. During this time, the voltage on the APD in a microcell is restoring back to the bias voltage. The RC time constant of the slow component, which is effectively an exponential decay, is proportional to the microcell size. It takes about 5 times RC times for a microcell to recover to its quote-unquote ready state. This recovery time will range, depending on the microcell size, from tens to even hundreds of nanoseconds. As we stated before, an SiPM is effectively a current source. If illuminated by photons, the output consists of chronological superposition of current pulses. However, if I were to observe the output of a SiPM even under no light conditions or in complete darkness, I would still see pulses flowing out of the anode. These are dark pulses, or dark current, or dark counts. Thus, as shown in this slide, the output consists, say in presence of light, of both pulses due to light, photons, and due to dark events within SiPM. The rate of dark counts depends on overvoltage, temperature, and the size of the active area. If I were to closely observe pulses coming out of SiPM, every so often I would observe pulses that have twice or even 3 times the amplitude of 1 PE waveforms. These pulses or these waveforms are likely due to a phenomenon which is unique to SiPM known as crosstalk. As shown on the left-hand side, suppose that I have a primary discharge, maybe induced by a photon or a dark electron. This primary discharge can cause a secondary discharge almost simultaneous in neighboring pixel. As a result, therefore, we are going to get 2 PE or 3 PE if the discharges occur in 2 nearby pixels. This is a crosstalk again, and an example of what we call correlated noise. One can operate SiPM in 2 modes. If the light level is low, so that the current pulses are distinguishable from each other, one can simply count these pulses. This mode of operation is known as photon counting or digital mode, and it has many advantages. For example, it's less sensitive, or the results of the counting are less sensitive to gain variations. However, if the light level is high enough so that the pulses overlap, one can operate SiPM in so-called analog mode, where one measures the output average current or voltage. Every photodetector must be biased, and also there has to be a detection electronics. This slide shows 2 possible biasing and detection circuits. There are more, but these are the most common ones. On the left-hand side, we see a circuit where the output of SiPM, or the current pulse, is converted to voltage pulse through the load resistor, and then that voltage pulse is amplified by the voltage amplifier. And so here the output signal is voltage. The R and C are parts of the biasing circuit. On the right-hand side, we see a circuit that employs transimpedance amplifier. Again, here there is a conversion of current to voltage through this classic electronic circuit. Let us now turn our attention to performance and characteristics. In the next few slides, I'm going to discuss characteristics such as photon detection efficiency, gain, temperature effects, crosstalk probability, dark current, and linearity. The slides I'm going to show you will contain plots that the manufacturer of SiPMs is likely to present in their data sheets. Let's start with photon detection efficiency, which is simply a probability that incident photon on the active area is actually detected. Here we see a plot of PDE as a function of wavelength. This is the most fundamental characteristic of any photodetector. As we can see, the photon detection efficiency depends on wavelength, but also, quite surprisingly, it depends on overvoltage. Thus, please note that this chart specifically says that it is obtained for 7 volts overvoltage. Photon detection efficiency also depends on microcell size. All else being equal, PDE will increase with microcell size because the fill factor increases as well. Looking at various charts of PDE as a function of wavelength, one can see that PDE will range somewhere between 20, or peak PDE will range between 20% and 50%. The producers of SiPMs have some degree of freedom to optimize SiPMs to various parts of electromagnetic spectrum. This figure shows a family of 3 PDE curves for SiPMs that are optimized to operate in near-infrared, visible, and UV part of electromagnetic spectrum. Let's now look at gain. So this plot shows a gain as a function of overvoltage. And we can see first from the y-axis or vertical axis that the gain for SiPM is on the order of 10 to 5, 10 to 6. Again, this is very high gain compared to other photodetectors except PMT. The plot also shows that the gain depends linearly on overvoltage. Any photodetector that has gain will also have so-called excess noise, which is, in essence, a penalty of having gain. In case of SiPM, that penalty is amazingly low. The excess noise figure is on the order of about 1.1 or so. This is actually quite fascinating for this detector. An often asked question is, does gain depend on temperature? This is a nuanced question, or perhaps I should say the answer is quite nuanced. So first, the answer is yes, if the bias voltage is fixed. So if I operate SiPM with fixed V bias and temperature changes, the gain is going to change, as shown by the figure on the right-hand side. Here, we fix the bias voltage at 55 volts, and as temperature changes, say from 40 degrees Celsius to minus 40, we can see that the gain can be reduced by a factor of 2. Why is this? The answer is that the breakdown voltage is a sensitive function of temperature, and therefore as the breakdown voltage changes, overvoltage changes, and therefore the gain changes. Thus, if I operate SiPM in such a way that the overvoltage is fixed, i.e., let's say I sense the temperature and then adjust the bias voltage so that the difference stays the same, in this case, the gain is independent of temperature. In many applications, we do not desire gain to change with temperature. We would like to have stable gain, and therefore one needs to have a circuitry that performs temperature compensation. Let's again look at crosstalk. Crosstalk is a phenomenon that cannot be eliminated. Some time ago, SiPMs exhibited another type of correlated noise known as afterpulsing. Afterpulsing has been reduced to irrelevance. Crosstalk probably will not be able to be reduced to irrelevance. So there will be always some crosstalk. And so here we see a plot of crosstalk as a function of overvoltage. And we see that the crosstalk monotonically increases with overvoltage. Crosstalk is the main contributor to excess noise. And one can write that F, the excess noise, is approximately equal to 1 plus probability of crosstalk. In this case, if I operate SiPM at 7 volts over voltage, the crosstalk will be only about 1.06 or so. Every photodetector exhibits dark current. SiPM is no exception, and thus the manufacturer provides information on dark current as a function of overvoltage. Please note that dark current will be also a function of temperature, and thus note that this particular curve is at 25 degrees Celsius. Very often, one would like to convert dark current into dark count rate, especially if one performs photon counting. For the given point circled with red circle, one can calculate dark current rate to be equal to a dark current divided by fundamental charge and the gain at that particular overvoltage. Doing quick math, one finds that dark current rate is about 520 kilohertz, or about one dark event per 2 microseconds. Linearity. For ideal photodetector, an ideal, which of course does not exist, the output signal, in this case current, would be linearly proportional to incident light level. No photodetector has perfect linearity, and SiPM is not an exception. So this plot shows the relationship between output and input. We can see that for low incident light levels, the linearity is quite good, but eventually deviates and flattens out. Here, where there is a flattening, we've reached saturation. This particular plot is for 850 nanometers. However, with some effort, one can transform this plot to any other wavelength. Very importantly, linearity of SiPM depends on the number of microcells for a given active area. In other words, if I have a given active area, let's say 6 by 6 millimeters, if I use smaller microcells, I'm going to have higher linearity. However, the penalty will be lower photon detection efficiency. Later in this webinar, I'm going to compare SiPM with a PMT and APD. And so therefore, I would like to take a few minutes to briefly review the operation of a PMT, an avalanche photodiode. Here at the bottom of this slide, we see pictures of a PMT on the left-hand side, which is a cold vacuum tube, and APD on the right-hand side. As already stated, PMT is a cold vacuum tube. It has three essential components: a photocathode, symbolized with letter K, a sequence of diodes, and an anode. All these components must be biased, i.e., electrical potential has to be applied to them. This is done by using a voltage divider, which is a separate part of a PMT. One has the freedom of using a variety of voltage dividers. A photon strikes a photocathode. Through photoelectric effect, an electron is emitted. This electron accelerates and strikes, let's say, the first diode. Through secondary electron emission, some number of electrons will be emitted, 3 or 4. Repeating this process over and over again, as many as I have diodes. Finally, at the anode, I can have million or so electrons from one. Those electrons flow out, and thus a signal is produced. Please note that for a PMT, the electrical signal or pulse flows into the anode. And so the polarity of the pulse is opposite of the polarity of the pulse for SiPM. In this slide, let me just briefly, with one sentence per each bullet, contrast the two detectors. Solid state versus vacuum tube technology. They have comparable gains. They have comparable excess noise. Dark count rate per unit active area is larger in SiPM. SiPMs are immune to the presence of electric and magnetic fields, external. This is not necessarily so for PMTs. They have comparable photosensitivity in spectral overlap region, though it's true that as a family, PMTs are sensitive to a wider part of electromagnetic spectrum. And there is a greater optimization for PMTs. So as we saw earlier in the presentation, there is some optimization possible for SiPMs, but it is not as great as for PMTs. Let's now look at APD. An APD is essentially a p-n junction, where in the depletion region, the electric field is sufficiently high so that when a photon creates electron-hole pair, these carriers are accelerated to sufficient energies that they can impact ionized silicon atoms and thus produce an avalanche. However, a normal APD, quote unquote, that operates in linear region will produce an avalanche that is self-quenching. So there is no external circuitry necessary to quench the avalanches. Comparing further the SiPM and APD, they differ in construction. The gain in SiPM is greater than gain in APD. In case of APD, the useful gain is up to about 100 or so, but it comes with great excess noise penalty. After this review, let's now look at possible applications of SiPMs. So I would like to make a comment that there are some optimal applications like PET, positron emission tomography. The three applications that I will discuss are those where SiPMs may be able to be used instead of the standard detectors. Let's begin with automotive time-of-flight LIDAR. The basic idea here is, suppose I have a self-driving car as shown in this slide. This self-driving car needs to know how far the objects around it are. For example, a tree. One can use LIDAR to find the distance to that tree. The physics concept is as follows. A source of light, a laser for example, produces a short duration pulse of light. At the moment of emission, it issues a start pulse, either directly from a laser or dedicated fast photodetector. The pulse travels to the target, reflects from the target, and the remaining light comes back and is projected onto a photodetector that detects the light and produces a stopped pulse. The stopped pulse stops the timer, and thus one measures round-trip time of flight, delta t. Range, or distance to the reflection point, therefore is equal to speed of light times delta t divided by 2. By rastering or scanning the surroundings, one can produce a 3D map, preferably at the video rate of 20 frames per second. What photodetector one uses for the received light will be predicated on the characteristics of received light. And so let's quickly go through the type of light that I expect at the detection photodetector. First, wavelength. There is still no consensus what wavelength should be used. However, two wavelengths stand out, 905 nanometers and 5050. Each has pros and cons, as often is the case in life. At this moment, there is no SiPM that is sensitive to 1550, though this may change in the future. The current ones can detect 905. The pulse duration should be as short as possible. Currently, they are in the range of 2 to 5 nanoseconds, so almost delta pulses of light. Number of photons per return pulse tends to be very low. So when we emit the pulse, number of photons in the pulse can be on the order of 10 to 20 to 22, a huge number. However, what we get back can range from hundreds to maybe tens of thousands. So the vast majority of photons do not come back from this round trip. Repetition frequency will range from kilohertz to megahertz, depending how rapidly we would like to obtain the 3D map. And of course, LiDAR has to be able to operate day and night, and therefore during the day we expect a DC photon background. Based on these characteristics, the photodetector requirements are as follows. It you should have high quantum efficiency at 905 or 1550. And this will help with the range and will also help in detecting weak light signals. You should have high detector intrinsic gain, which reduces the importance of electronic noise. This is the great advantage of having gain in the detector. One cannot supplement this gain with the gain of, let's say, voltage amplifier or transimpedance amplifier. You should have small excess noise and small time jitter. Both will affect timing error. APD has been a default detector. So the question is, can our very young, only maybe 20 years old SiPM be a possible or perhaps even better choice? I decided to answer this question by performing a side-by-side comparison between an SiPM that is marketed for this application and APD that is also marketed for this application. Let's begin with photon detection efficiency and quantum efficiency for APD, which are synonymous in this case to each other. We see that at 905 nanometers, the QE of APD is higher than that of SiPM. And so therefore in this case, APD has an advantage. And thus, a green here and red for SiPM. Now let's look at gain. For a reasonable overvoltage, the gain of SiPM will be on the order of 10 to 5, 10 to 6, very high. Whereas for APD, for a reasonable reverse voltage, the usable gain will be about up to 100. But as I mentioned earlier, typically it will be 50 or so. And so clearly here, SiPM has an advantage. A lower gain for APD will mean that we'll have to use a more expensive low noise electronics or detection electronics when APD is used. Excess noise. We already know about excess noise for SiPM, very low, about 1.1 or so. In case of APD, excess noise depends approximately on gain raised to 0.3 power. For 50 gain, the excess noise is 3.2, 3 times higher than excess noise for SiPM. Here, SiPM has great advantage. Finally, time jitter. There are two contributions to time jitter. One is the classical jitter, which is variation in response time. This time jitter is often expressed for a single photon illumination. And for SiPM and APDs, it's quite comparable and on the order of 100 picoseconds. However, there's another effect known as time walk effect. For a constant trigger level, timing depends on gain variation and signal intensity. As shown in the next slide, the red here represents a trigger level. Suppose I have a fixed illumination, but I have gain variation, i.e. I have excess noise. One can see that given this excess noise, the triggering will occur at different times, thus giving again error in distance measurement. Clearly, SiPM has great advantage over APD in this case. However, do note that even if I use SiPM, I still have a time walk effect because the signal level will generally vary in LiDAR application. Before we move on, some takeaway points. SiPMs are likely to compete successfully with APDs at 905 nanometers because of their higher gain and much lower excess noise. And empirical evidence is forthcoming. There are already publications becoming available that point to the fact that SiPM will tend to perform better. Sensitivity at 905 will improve in a new generation SiPMs. The manufacturers are very well aware of the importance of this wavelength for this very important application. SiPMs with sensitivity at 1550 are also being developed. And so the future generation SiPMs, we'll have to change the name. We cannot use silicon anymore, but they are likely to be extended to the infrared region. Let's now turn our attention to another application, possible application, flow cytometry. Flow cytometry is a technique where we study cells or interrogate cells using light. The basic idea is as follows. I have a capillary with some sheath fluid flowing. Into this flow, cells are injected in such a way that they flow one by one in a linear manner. A certain point in the capillary is illuminated by light from a laser or lasers. It doesn't have to be one wavelength. There could be multiple wavelengths at a time. As the cell passes the interrogation point, it's going to scatter light in all directions. How it scatters the light will depend on its size, its structure, its complexity, its index of refraction. Typically, we place two detectors, one in the forward direction and another one in the perpendicular direction, referred to as side scatter photodetector. Modern flow cytometers also use fluorescence. In this case, before injecting cells into the flow, dye molecules are attached to them. And as they pass, the laser light may excite these molecules, producing fluorescent light. The most fundamental plot in flow cytometry is the plot of side scatter signal versus forward scatter signal. As I said, this is the fundamental plot, but there are many other possible, especially when one has fluorescence. One can plot one fluorescent signal versus another, or versus forward scatter, so there are a number of possibilities. We can see in this cartoon version of such plot that when I have three different populations of cells, they're going to group in different regions of the plot. This is how we can identify them and perhaps even sort them, as many flow cytometers do. Let's now review the characteristics of received light. First, wavelength. The wavelength can be selected depending on the cell size and fluorescence. As I mentioned already, one can employ multiple lasers at the same time. Even though the illumination is DC, what we are going to receive are pulses. And that's because a cell passes through the interrogation point. This is when light is scattered. The duration of these pulses will depend on the sheath flow speed and the cell size, and it's on the order of microseconds. The number of photons per pulse will vary from few to thousands of photons. And so therefore we expect a very high dynamic range of the photonic signal. And the rate of pulses is going to be on the order of kilohertz. Again, this will depend on the rate of the sheath flow. Based on these characteristics, the side scatter photodetector requirements are, but before I list them, the forward scatter signal tends to be strong, and thus there one uses an inexpensive, a photodiode. I didn't mean to say inexpensive, a photodiode or avalanche photodiode. There is plenty of signal to use these devices with either no gain or little gain. However, for side scatter photodetector, where there is relatively much less light going, one needs to use a photodetector which is going to have a gain. But let's go to the list. So again, we like to have high photon detection efficiency. This will affect the signal to noise of the detection. High intrinsic gain, as before, to reduce the importance of electronic noise. We'd like to have minimal excess noise because this noise would introduce distortions in our histograms. We'd like to have linearity for the same reason. And we'd like to have high dynamic range because we expect signal to vary from few photons to thousands of them. The most commonly used photodetector was or is still photomultiplier tube. And so again, the same question as before. Could I use silicon photomultiplier instead? And you may wonder, why would I want to do that? And that's because SiPM has some advantages over PMTs that I perhaps did not enumerate very explicitly in this presentation. And therefore one could be tempted to make the switch. So let's see if such switch is possible and rational. So let's again compare side by side an SiPM that is marketed for flow cytometry and a PMT which is part of a module which is used in flow cytometers. Let's begin by efficiency of detection. And I chose a particular wavelength of 450 nanometers. We can see that PD for this SiPM with over 14,000 microcells has a PDE of about 25 or so percent at 450. In case of PMT, their corresponding QE at the same wavelength is about 28%. This has to be derived because what's given here in the plot is cathode radiance sensitivity, but one can calculate the corresponding QE. And so one can see that photosensitivities are quite similar, so no loser or winner in this case. Let's go to the gain, and again we can see that the gains are quite comparable. In case of a PMT, the gain is controlled by the control voltage. This is the control voltage that controls the module. The voltage on the PMT still is going to be on the order of 1,000 volts or so. And so the gains are, again, quite comparable. So no advantage for either side. We already talked about excess noise for SiPM. In case of a PMT, the excess noise is approximately given by delta divided by delta minus 1, where delta is the gain of the first dynode, which is typically on the order of 4, 5. And so doing the math, one finds that the excess noise for a PMT will be about 1.2 or so. And so slight advantage to SiPM. But now let's discuss linearity and the related idea of dynamic range. For a PMT, the linearity and dynamic range can be changed or adjusted or shifted using a voltage divider and the supply voltage. And so here we see a pulse linearity characteristic deviation as a function of output current. This is again for pulse, so this will be peak current in a pulse. This plot is obtained using pulses of 500 nanosecond duration with a repetition period or frequency of 1 kilohertz. One can see that the linearity curve depends on the control voltage. I chose a single point shown in red for control voltage of 1 where linearity deviates by 10%. And I calculated the number of photons in the pulse assuming 450 nanometers. And that is about 4.2 times 10 to 5 photons. So such pulse for a PMT would produce 10% nonlinearity. What I did then is to use SiPM, the one that we are discussing, and calculate its nonlinearity. In case of an SiPM, the ideal response, the perfect response, would be the number of photons in the pulse times photon detection efficiency. However, this will be an ideal case. In a realistic case, the number of fired microcells is given by this equation, where N total is total number of microcells, TP is the pulse duration, and TR is recovery time. Plugging numbers in, I find that nonlinearity is 32%. And so clearly SiPM performs worse compared to a PMT. However, I would like to point out that if I were to use a control voltage of 0.5 volts for a PMT, and if I were to extrapolate this curve I would find that the linearity there would be also about 30% or so. Before we move on, some takeaway points. First, the major weakness of SiPMs in flow cytometry is limited dynamic range and linearity. However, out of dozens of optical channels in the flow cytometer, SiPM can be possibly used for some, probably not for all of them, but it's likely that there will be some channels where SiPM will be suitable. There is a great interest in using SiPMs in flow cytometry, but what I found rather surprising is that there is very little published work on this subject. Let us now discuss radiation monitoring and spectroscopy. These are related but somehow different ideas in radiation detection. First, monitoring. So the basic idea here is to detect radiation that the photodetector is directly not sensitive to, like for example high energy electrons, protons, or gamma rays. Here we are interested to know whether such radiation exists or not, and would like to know its flux or the rate. To do so, one can use a photodetector like SiPM or PMT with a scintillator. The role of the scintillator is to convert energy of ionizing radiation to photons that the photodetector can detect. The basic setup is as follows. We have a scintillator, a photodetector, amplifier, a discriminator, and the counter. So again, it's used to detect the presence of specific radiation. Monitoring devices are often portable and handheld, and the information it's provided here is radiation rate, from which we can derive flux. Let's look now at the characteristics of received light. The wavelength will depend on the choice of the scintillator, but often it is in the range of 300 to 500 nanometer, so visible. We are going to have pulses. The number of photons per pulse will depend on energy of ionizing radiation and type of a scintillator. Duration of these pulses will depend on the size and type of scintillator, where the decay time constants can range from nanoseconds to microseconds. And frequency of pulses depends on the rate of incoming radiation. Based on these characteristics, we would like to have, again, photodetector with high photon detection efficiency. I guess this item is always at the top. Higher QE is always better. We'd like to have high intrinsic gain, again, to minimize the importance of electronic noise. Large active area to couple to the scintillator. Ability to couple to scintillator. And in this case, the photodetector should be suitable for portable and handheld devices. A somewhat related issue is radiation spectroscopy. In this case, we certainly want to detect radiation, but also we'd like to know how much energy this radiation has. Thus, I would like to perform or construct a radiation spectrum. To do so now, I have to measure how much light was released in the scintillation event. To do so, one commonly uses a charge integrator shown on this slide. The basic setup is as follows. One has a scintillator photodetector, charge integrator, voltage to voltage amplifier, discriminator, A to D converter, and the computer, which will then display a histogram or a spectrum, which plots number of events as a function of energy. And the peaks that we see here will correspond to radiation, in this case with two specific energies. How well we resolve these peaks is measured by so-called resolution, which is equal to full width half max of the peak divided by the energy of that peak. This resolution is a function of properties of the photodetector and scintillator, so both are going to contribute to the width of that peak. For this application, we would like, again, photodetector to have high quantum efficiency, but I'm repeating myself, high intrinsic gain for the same reasons as before. Low excess noise, which will affect the resolution, high linearity, and ability to couple to scintillators. In these areas, PMTs used to dominate the detector choice in radiation detection, monitoring, and spectroscopy. However, SiPMs are becoming a viable alternative. However, due to a multitude of possible detection scenarios, it is best in this case to perform a side-by-side empirical comparison between SiPM and a PMT. So it's not good enough to just take data sheets for SiPM and PMT and look at them side by side. The best thing is to go to a lab and perform the comparison. There are numerous studies in the literature that did just that. I would like to bring your attention to a very recent one, work by Grodzicka et al., who compares side by side SiPM and PMT for a gamma ray detection. They use a variety of energies and variety of scintillators. Here is an example of spectrum on left-hand side for SiPM and on right-hand side for a PMT. In the same study, one sees a table where energy resolution for SiPM and PMT are listed, again for different scintillators and different energies. Looking at these numbers, one sees that in general, PMTs perform better, but not substantially better. And so therefore, given desirable characteristics of SiPM, many groups in high energy physics, high energy astrophysics, and other areas do indeed switch from PMTs to SiPMs if, again, possible. Some takeaway points for this application. SiPMs provide comparable performance to PMTs in radiation monitoring and spectroscopy. It is likely that the majority of handheld devices will employ SiPMs. And side-by-side comparison is the best approach in deciding if an SiPM or a PMT should be used for a given detection application. Let me summarize briefly this webinar. High gain, low excess noise, magnetic immunity, and ease of use are some of the highly desirable characteristics of SiPMs. I should add to this low biasing voltage, which is on the order of only tenths of volts. There is a great interest in using SiPMs instead of APDs and PMTs in a variety of applications. The new generation SiPMs will have improved characteristics, making the transition more likely. Again, I would like to remind the audience that SiPMs were developed in mid-90s, so they are only about 20 years old devices, whereas PMT, for example, is more than a century-old device. The new generation SiPMs will only get better. I'd like to make one more point. Hamamatsu Corporation, which I represent, manufactures both SiPMs, PMTs, and APDs, and therefore this company is a great source of unbiased information on these three detectors and more. Before I formally finish the presentation, let me point that Hamamatsu will be presenting at booth 521 at Photonics West 18, and in addition to that, it's going to sponsor a number of oral presentations, and one of them, a day-long webinar workshop, will be given by me. I would like to thank everyone for logging in, for listening to this webinar. I greatly appreciate. Again, this is Slawomir Piatek. Thank you very much. Back to you, John.
Thank you, Slawomir. We're now in the Q&A portion of the webcast. So once again, to ask a question, click on the Ask a Question icon in the presentation window. As the Q&A starts, we do have one more very short survey for you to fill out, which you will see momentarily and can fill out as you listen to the Q&A. So our first question: When comparing different SiPMs from various vendors, should I compare the specification directly listed on the datasheet and/or catalog?
So maybe I will answer this question there. I do have some backup here, but let me answer this question. The answer is yes, if one compares apples to apples. However, when one looks at data sheets from various manufacturers, one can see that, for example, dark current curves or, say, photon detection efficiency curves are taken at different conditions. As we learned in this presentation, for example, dark current is not only a function of temperature, but over voltage. So there are a number of parameters that come to play. So as long as one is certain that one is comparing exactly the characteristics taken at exactly the same conditions, then the answer will be yes. However, rarely one has such ideal situation. So the best approach, in my view, is to contact manufacturers directly with specific questions.
Okay, and I did want to mention that we have limited time, so I'm going to ask 2 more questions. I do want to tell the audience that there are a lot of questions that we received. Unfortunately, though, we can't answer them on air. They will all be sent to Slawomir, and he can answer them at his leisure via email. So hope you don't feel ignored if they're not answered on the air, because you will get a response. So second question, is temperature compensation absolutely necessary?
So again, let me answer this question. Okay, so if one operates SiPM in an environment where temperature is stable, then the answer is no. However, if temperature changes and the particular application does not tolerate gain variation, then one needs to use a circuit with temperature compensation, as discussed in the webinar. So such circuit is going to sense the temperature and then adjust the bias voltage to keep the over voltage fixed. Please note that here we are going to stabilize the gain, but we are not going to stabilize a dark current. Dark current will go up or down depending on the temperature. So the most ideal solution will be to stabilize the temperature, but I do understand that in some situations, like for handheld devices, this may be very difficult to do.
Okay, and the final question. What is your opinion about the additional fast output signal mode found in SiPMs from competitors? Drawbacks, advantages?
Okay, that fast output is actually a consequence of so-called parasitic capacitance on the quenching resistor. So it's not really by design. It's in some sense, I don't want to call it noise, but it's due to parasitic capacitance. One can employ it to one's advantages if it's present, but it doesn't always have to be present. And also, please note that whether one sees that spike or not depends on the detection bandwidth.
Okay. That wraps up the Q&A portion of the presentation, but Slawomir, I'd like to ask if you have any closing remarks.
I would like to again thank the audience. We had a very high subscription rate, so I appreciate the attention that the community pays to our webinars at Hamamatsu. So I'm very much appreciative of the attention. So again, I would like to thank everyone for attending the webinar.
Yes, this is a very well-attended webcast, so there are a lot of people out there who want to know about more about SiPMs. So on behalf of Laser Focus World and Hamamatsu Corporation, I'd like to thank today's speaker, Slawomir Piatek of Hamamatsu, for today's presentation, the silicon photomultiplier operation, performance, and possible applications. And as I noted before, for those in the audience who want a copy of today's slides, a PDF of today's presentation is available in the event resources section below the Q&A box. This presentation will be archived within 24 hours and can be reached from our homepage at www.laserfocusworld.com. A reminder email message will be sent to all registrants complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.
Thank you.